Is the screen sharing working? Do you see the screen?
Yes, we see everything. So please go ahead, Melise.
Sorry?
Please go ahead, Melise.
Oh, yeah, sure. Well, welcome everyone. Thank you guys for joining in person. And I see that we have a good attendance online as well, so that's great. That's a great pleasure today for me to welcome Valentin. So he's a postdoctoral fellow at NASA Ames Research Center in California. And he's with us for the whole week because he's actually taking part to the ALMA ambassador program. So we're both spending the week at NARIO getting a training on like new ALMA capabilities and so on. So he's going to be around until Friday, and we don't have anything on the schedule on Friday. So well, it doesn't matter for you online, but if people here want to get a chance to talk to him in person, just let him know. And he's going to tell us today about his main, research, which is, correct me if I'm wrong, but on the low mass star formation using observations of dust polarization emission. But you will talk about it much better than I do. So please go ahead. Floor is yours.
Thank you, Melise. Thank you, Jonathan, for inviting me. So yeah, I'll go ahead. I will present actually my work, which now expanded a bit in wavelengths. I'm trying to associate both the 7mm and the infrared observation to address the question of how do stars form, especially low mass and nearby objects. All right, so just here, basic example of star forming regions, serpent stars. On the left, you see a Spitzer image, Iraq, and on the right, you see a 7mm image. You see that in the infrared, you're mostly affected by extension, but you do see protostars here, class 1 and 0 appearing in pink dots, and this corresponds to where the mass is. The densest, the protostar form at the densest location in molecular clouds, and this is where we observe them. So here is the accepted prototypical sequence of low mass star formation. Today we'll focus on the protostellar phase, which comes after the prestellar core phase and before the stage where you only remain with a disk and forming planets. So the protostellar phase is this phase where most of the accretion onto the central object is happening, and this is what I'm studied in my research. How does this accretion happen? How do you get rid of the angular momentum to explain the distribution of the angular momentum of stars? Especially the class 0 phase, very interesting because it is thought that most of the accretion is happening in this phase. This phase is characterized by acidic classification. It's mostly, these objects are mostly characterized by a very red and acid, mainly corresponding to mainly a very extended envelope, so dense and cold envelope emitting in the infrared and millimeter wavelengths. And this stage is characterized by several key questions in star formation that I'm trying to address. Here, they're all listed here. First, the collapse. So we don't really have a clear or complete understanding on how the collapse proceeds. Is that homogeneous? Is that symmetric, or is it super disorganized? And can we explain the early multiplicity of protostar with the level of organization of the collapse? It's one of the questions I'm trying to answer. So we observe envelope, we observe how the accretion is organized in the form of streamers or not. We observe the role of magnetic fields in the envelope to see their action threading the disk formation. Ultimately, we also want to measure accretion onto the central object. So several techniques are possible, but the young protostars are make it very difficult because they're super extended. So measurement of the accretion is challenging. However, we tend to really think, as I said before, that most of the accretion is happening in the early stage, and this is indicated by such example of surveys of H1 line measured in the infrared that we use to compute the accretion luminosity. And as you can see here, class 1 are brighter and in H1, and the accretion luminosity is higher than typical T-Tauri stars. But now the next challenge would be to do this survey for early phase for even more embedded objects. Another question I'm trying to address is the ejection. So as I said, we need to get rid of some amount of angular momentum to explain the decrease by several orders of magnitude of angular momentum between the one of the cloud down to the one of the stars. And this must happen during the formation of the disk and during the accretion of material onto the star. And outflow are a good candidate to extract this excess of angular momentum. Dust evolution. So dust is also thought to evolve a lot in this phase. We need to understand how dust evolves from a typical ISM dust type grains to the pebbles and planetesimal we expect to encounter in disks. And so this protostellar phase is the junction, right? The intermediate step of dust evolution. And that's it. Okay. And all of these questions are all related somehow to the magnetic field. And this is like the running point I'm trying to make during this talk is that magnetic fields are involved in all of these phenomena. Here you have an example of an observation of magnetic fields of a classical core on the left and an MHD model representing what's happening. So the magnetic field interact with the collapsing matter. They redistribute the angular momentum along the collapse, and they regulate the size and disk, the size and mass of disk via this effect of magnetic braking. How is that related to dust? Well, because the ion recombination rate is totally governed by the recombination of ions onto dust grains. In this cold and dense region, most of the charge carriers are actually the dust, because ions don't survive. They just recombine too easily. So the interaction between the magnetic field and the matter is governed by the small dust, and therefore understanding dust evolution makes us understand the coupling between magnetic field and matter, and therefore the role of magnetic field regulating the angular momentum. So to understand the role of magnetic field, you basically need to have a good idea of what the dust size distribution. So it's all linked. This question of accretion, dust properties, it's all very much linked. If you look at MHD models implementing this this evolution of coupling between matter and B field, you see that indeed the magnetization is important. It has a key effect on the subsequent disk formation, whether you evolve the magnetization or the alignment between magnetic field and angular momentum, the disk you will form in the MHD model is very much different. And this is the thing we're trying to observe it in observation, to relate the disk with the properties of the magnetic field. All right, and how do we do this? Well, we observe with ALMA, we observe protostars with ALMA, looking at the dust thermal emission surrounding the disk, surrounding the central object, so the envelope. And because the grains are aspherical and they tend to keep the same axis of spinning with time, the thermal emission is linearly polarized with respect to the rotation axis. And this rotation axis ends up being parallel to a magnetic field line because of this grain alignment mechanism. Basically, photons interact with those grains, give them momentum, and via internal relaxation effect, you align paramagnetic material with the magnetic field. And so we observe with ALMA maps of magnetic field projected onto the plane of the sky of protostars. And here you have a gallery of observation that now have been obtained since 2018, and these are the most detailed maps of magnetic field we have of star forming object right now. Again, this is low to intermediate mass protostar within 500 parsecs. And here you have the outflow cavities. As I said, most of the objects develop bipolar outflow ejected from the center. So you can see here that the magnetic field has a lot of different morphologies that ultimately correspond to a lot of different collapse. Some are very symmetric and are suggestive of a collapse pretty much organized by the magnetic field, where material would follow the field line and control the accretion this way. Some objects are heavily fragmented and with a pretty disorganized magnetic field, not necessarily symmetric. And this case are most suggestive of a turbulent collapse, where the accretion is more resulting of disorganized motion, so a higher initial level of turbulence.
That's a quick question about
Yes,
that plot.
okay.
So for the BHR71 versus NGC1333, why are the lines kind of wider or bolder on the one on the left versus the one further to the right? Is that just the scale, or is that because the magnetic field properties are different?
It's just the beam is just much smaller in this case.
Oh, okay. Okay.
So you have
Yeah.
10 times more vector.
Okay. Thank you. Yeah.
It's
Yeah.
just a floating thing.
Okay.
But we all of these observation kind of target the same spatial scales, right? The beam is about between 50 to 200 AU, which really correspond to the bulk of the mass of class 0 envelope located in substructure, because ALMA is an interferometer, so we observe the substructure, the dense substructure of cores that correspond to allegedly the location of the envelope where most of the mass infall rate happened, right? It is called accretion streamers that we observed in all of these objects. Like here, for example, this dense streamer for BHR71 and RS1 are thought to channel most of the mass infall rate. And so this dichotomy I just said can actually, again, be related with the level of organization in the collapse. And this dichotomy is just illustrated here with two imaging models implementing different level of initial turbulence with respect to B field strength. And you can see that indeed, in the case of a collapse where the magnetic field controls everything, the collapse is symmetric and the accretion rate is governed by this slow evolving collapse. And well, in the case of the turbulent collapse, it's more disorganized. The accretion rate is actually higher in the early times of the sink particle at the center. And so this really suggests that to understand the accretion and deformation at this stage, we need to map the initial condition of core collapse, whether they are B field regulated or more turbulent with the subdominant action of B fields. And this is what we are trying to do right now with statistics, addressing this question toward a large number of ALMA observations of protostar. So and doing this on the multi-scale. Yeah, here you have an example of two cores again, showing this falling into this dichotomy of a case where the collapse is symmetric, isolated, and what the magnetic field lines is conserved through scales, and another one where you form a cluster of cores. Your B field line are much more disorganized. Here you can see clearly spiral arms and tidal effects, and so these different modes of protostellar core evolution are meant to be characterized by statistics, and we are now increasing the number of ALMA observation, now reaching nearly 100 cores observed, and our goal will be to map the evolution of magnetic field with scales with way to quantify the evolution of the core, which could be the disk mass, the multiplicity, the organization of structures, how symmetric are the structures, and this way we'll quantify how the spectrum of magnetization of star forming cores in nearby clouds. All right, now now I'm going on the dust evolution side of things, and because observing all of this B field map, we observe dust polarization and therefore grain alignment physics. We quantify grain alignment physics, and this is also a nice way to map to understand the evolution of those grains in protostellar envelope, because the grain alignment is sensitive to the maximum grain size, which means it's sensitive to the grain growth in this early phase of star formation. Here on the left, you can see a diagram showing the grain alignment efficiency versus the density, and this for different maximum dust grain size. And colors are models of star forming cores compared to ALMA level of grain alignment efficiency. And you can see that on average, you need to implement large dust grains compared to typical ISM to reproduce the grain alignment efficiency. So using this polarization, you can probe dust grain growth in class 0 cores and map this intermediate step of grain growth between ISM dust grains and the large millimeter grains you see in protoplanetary disks. And this can be explained by the fact that to interact with light and get a line, dust grains needs to be on the order of the wavelengths in size. And because photons are mostly infrared, dust grain must be at least super micrometric to get a line. And because we see high-line grains, they must be large. That's the reasoning behind this discovery of large grains in envelopes. Now, the important question is to understand where do they grow. To close the loop of this question of dust grain evolution, whether they form in the disk, and we know whether they grow in the disk, and we know they grow in disk because it's super dense and cold, or they grow in situ during the collapse. If they grow if they grow in situ in the collapse, when the model of the grain evolution must reproduce this, and right now they are not quite there yet, but it's a field in progress. If dust grain grow in disk, we need to explain how can they repopulate the envelope. Maybe they get transported by the outflow by just the drag forces induced by the gaseous outflow. And in this case, when we need to justify how dust grain can survive the fragmentation in outflow cavities.
Can I ask a question real quick?
Sure.
So for the two plots over there, you're showing that it's either infalling material or material and train going outwards, right? But
yeah,
how do we know it's infalling or outgoing just from the plots?
We don't know. I mean, it's just no, it's just.
It's just demonstrated
to represent things, but you're right. You don't know. In this case, we have gas kinematics, and we know it's infalling. In this northern case, in the southern case, we know that the gas kinematics suggest more an outflowing material where we see aligned grains, because this is where we know there is large grains. But no, it was just otherwise to illustrate the point. Okay, one thing that we did, so I just showed that we compared models with observation of ALMA. Well, this is detailed actually here to study the grain alignment efficiency in cores and compare that to ALMA. We take MHD models. Here in this case, Ramses. We post-process them with a polarization radiative transfer. We filter the model with artificial interferometric filtering, and then we compare with ALMA. We compare the grain alignment efficiency with ALMA data. And one thing that we found is that actually the filtering has some effect on the polarization quantity, they tend to artificially increase the polarization quantity, because when you think of it, Stokes I has a typical power spectrum. Stokes Q and U have a different one because the power spectrum depends on the power spectrum of Stokes I plus the power spectrum of the morphology of magnetic field and how it depends with scales. And therefore, when you filter them with ALMA, you artificially change your polarization fraction, which is Q and U over I, and this is where you bias your level of polarization fraction, and this must be taken into account when comparing models to ALMA data. And then just this plot illustrates this point here. When you see the effect at low column density, you can see the effect of filtering. All right. Now another thing we've looked at, studying the grain alignment efficiency and the properties of the environment where we see aligned as grains, is the irradiation and the level of irradiation, especially in outflow cavities. And again, this is also linked with the global picture, because irradiation here comes mostly from the accretion luminosity and therefore the actual accretion rate onto the center. So we found that comparing irradiative sensitive chemistry with the polarization, we found that actually the irradiation field is a key ingredient in aligning those grains, and therefore the accretion onto the center is actually directly responsible for the heating of the core, and therefore the grain alignment that we observe. However, it's also important to understand other sources of heating, and when looking at outflow, the mechanical heating must be also important in sublocation towards shocks. For example, we do see dust polarized emission enhanced where there is shocks, like here traced by ESO. ESO is a shock tracer in outflow cavities, and in a few locations, the dust polarization match very well location of shocks. So this means that the mechanical heating is also important, and that both mechanical energy and irradiative energy account here in the global feedback effect triggered by the accretion. All right, and this is quantified also in models where we compare the irradiation level, where we compare 4 different irradiation levels. Again, the grain alignment efficiency in this upper plot here, again showing that you need to implement a significant level of irradiation and therefore of accretion luminosity in force to reproduce the grain alignment efficiency. So the grain alignment, the polarization that we observe in protostars is actually a trace, an indirect trace of the accretion luminosity in the core, and therefore it's a super efficient diagnostic for the evolution of the object, and how does the accretion evolve also with time, for example. So just to say that the polarization is a very interesting tool, because sensitive to many things, dust evolution and accretion properties.
If you had like 100 of these class 0 protostars and made a plot of like polarization, signal or strength, whatever the best way, would it correlate with accretion luminosity, you think, or is that maybe a future proposal to do? Or
yeah, no, that's the thing we are trying to do now.
Yeah.
We are trying to compare this level of polarization with diagnostics related to accretion.
Yeah.
The luminosity, the disk mass.
Yeah.
All of this will eventually come together. Yeah.
Okay. Thanks.
Now, just for a few slides now, I will just address one problem of this nice story, which is the fragmentation of this grain. And this is actually something that comes at odds with all of this first story. That if we need to have large grains, and we need to have them to get them spin up efficiently to explain the dust polarization. However, If they're large, if they're spin fast, they can disrupt. It's called the rotational disruption of grains. If the centrifugal forces exceed the cohesion force, those grains disrupt, and then you repopulate your small grains, you increase the recombination with ions, and then your non-MHD effect gets changed, and everything, it can have a huge impact in the dynamics in the dynamics of the inner core if you repopulate the small grains. So we've tried to quantify this effect as a function of the grain tensile strength. And you can see an example of this of our result here, where we see that actually only outflow cavities are sensitive to this effect. So basically, this means that if large grains are ejected in outflow cavities, they will likely not survive because they would get rotational disrupted. And this also suggests that large dust grains are formed in the envelope and in the disk, but they're not ejected backwards in the envelope via outflow cavities. And to quantify this effect, we led a study toward the Orion bar, because it's a PDR that's super heavily irradiated by the trapezium cluster, and also because the far infrared is the ideal place to look at the alignment of small grains. So we looked at the Orion bar with Sophia using Hall Plus at 4 different wavelengths: 53, 89, 154, 214. We looked at the dust polarization, and we modeled the grain alignment with an analytical model, and we tried to see if and we tried to quantify this rotational disruption to see if we can understand it better, to see if it is actually really happening or not. And we found that so first, those grains are not aligned with the irradiation field. This was expected, but I can come back on it later. So, but comparing the grain alignment theory with the observation, we indeed found that the rotational disruption is likely happening in the very inner edge of the PDR, where the irradiation is very high. So this is quantified here by the gray region. In each boxes is a location along the Orion bar, and the x-axis is the position across the bar, with the right pointing toward the irradiation front. And we quantified this effects of rotational disruption, and the gray regions points toward the grain size affected by this effect. And we try also to link that with the actual dust distribution you can constrain using LCD, because the Orion bar has been observed in all wavelengths. We have a clearly defined LCD, and if this disruption were to be efficient, all the large aligned grains would be destroyed, and we would see an excess of small grains in the bar. And we try to see if we see such excess, measuring the mean infrared slope. And you can see how here on a CD that if you change the maximum size of silicate, you indeed repopulate small grains, and you see an excess in the mean infrared. So we computed the mean infrared slope versus the minimum size of disrupted dust grains in the bar. And we indeed see this little correlation here for a very hot region, indicative of a depletion of large silicates. This is just a tentative correlation here or study, but this would be the confirmation, if it is meant to be confirmed, that indeed this rotational disruption is efficient at removing the large grains in the layers of intensively irradiated PDR. And outflow cavities behave like pseudo PDR things, so this comparison is valid. All right. This is now the global picture. Slide. How much time do I have left? You don't know?
Well, maybe 3 or 4 minutes, if it's okay. Then we can have an extended discussion.
That's very bad. Anyway, okay. Now,
Okay.
I'm kidding. In the remaining 5 minutes, I will try to show the near-infrared side of things and how it is heavily complementary to this first outline I just did. I talked about accretion. I talked about how is the collapse organized. I talked about the properties of dust grains. Well, the actual accretion diagnostics are usually made in the near-infrared, but because class 0 and very embedded, it's hard to do. But we did so for a new sample, looking at the brightest class 0 in the infrared, looking at all the gold belt star forming clouds. We found a sample of class 0 bright enough to be observed by Keck. And this is, so here you can see the largest sample of class 0 observed in the K band with the medium resolution using Keck fire. And we observed many interesting things that seems to be prototypical of this very young protostellar stage. Love H2 bracket gamma is seen in more than half of the objects. CO overtone emission is seen in half of the objects. And we also see the photosphere. So we see a few photosphere corresponding to the central protostellar embryos. So it's very exciting because we're really probing the first stage of star formation, and it corresponds to a very intense accretion disk, an intense accretion. And we in this sample we quantified this accretion and showed that it is actually much more vigorous and outbursting in the class 0 phase compared to the class 1 phase, which is more evolved object. So here you have a comparison, for example, of different lines, and comparing detection rates between this class 0 sample with archival class 1. And you can see that the most striking one is the CO of emission, corresponding to very dense and very hot inner disk. This emission is much more frequent in class 0, meaning that the class 0 inner disk are much more active. And this is really quantified in such plot where I showed the CDF of the CO overtone luminosity versus and the bracket gamma luminosity for class 1 in blue and class 0 in red, and with also the 2 statistical tests here. So basically we probe that the accretion is more vigorous in a class 0 phase. On average, the accretion traces are brighter. So there's still some work that needs to be done quantifying precisely the extension of a class 0, because it's a very difficult thing. But this result also holds using just the equivalent width of lines. And so we try to quantify that with the statistical test and converge toward the fact that indeed class 0 tends to have much brighter accretion traces. And now just 1 or 2 slides on what JWST is actually bringing for this question of class 0 accretion. So JWST has unprecedented capabilities, and even compared to Keck, the sensitivity is just not comparable. So we are able to probe the near-infrared spectra with very high sensitivity, and therefore we can really target a much larger number of class 0 and study the accretion properties. Here just an example of a class 0 core. The grayscale is ALMA data, and you see it's an envelope fragmented in 4 cores. 2 of them are bright in the K band. Here it's a UKT image. And with JWST, we targeted the two central objects, and we found super interesting. Protostellar features. the continuum of the two James Webb source, as you can see in the contours here, so they not perfectly match the ALMA emission, and this is in itself interesting. Like this northern source, the disk in this northern source seen is ALMA correspond to the near infrared source, but not in the south. And in the south, in the near infrared we seem to mostly trace scattered light, not directly related with the disk that you see here. When you look at the spectra, it's also a very different behavior, and just in itself interesting to study. We see in the northern source a photosphere. As you can see here, we probe several absorption lines. So we see the photosphere of the class 0 protostellar embryo. And in the southern line, in the southern source, we mostly see emission. There is no continuum. The extension is just too high, given how embedded is the core. One source in the south here launches CO fundamental wind, while the one in the north doesn't. So you can see it's just an example of how this example shows the variety of near-infrared properties for protostar, and comparing James Webb with ALMA data gives us a huge synergy, because with the ALMA we know where is the mass, we know where the disk, we know where are the fragments, and with James Webb we actually can quantify the properties, whether it is in high accretion state or not, whether we see the photosphere, how young is the photosphere, etc. So just example here, as I said, here is an example of an H2 line, the CO wind in the southern source. We are working on it to quantify the short condition for H2, the LT condition for the CO wind. So this is all work in progress, and all work made possible by James Webb right now. And the last thing about actually the photosphere in the northern source. So as I said, we observed we can observe photosphere absorption features, and because we look at class 0, we also may look at the youngest ever star forming object, ever probed. And here it's an example of a model fitting of the photosphere, and we obtained a constraint on the surface gravity of 2, which is incredibly low, and so this really suggests that indeed we are looking toward an object that is super young and that just formed. And to give you an idea, class 1 has a surface gravity of 3 to 4. So we are really observing the very first nascent stellar core of the future star. Okay, and I'm finishing here. Sorry. Conclusions. So I talked about the mining field, the role in the collapse. We start to probe for the first time the accretion properties of the youngest and most embedded object with Keck and James Webb. We're gonna study the ejection properties of this object, looking at outflow, modeling shocks in cavity walls and jets, and the dust evolution is actually the ingredient that links everything up, because it really is responsible for the coupling between magnetic field and matter, and therefore it's responsible for how the magnetic field affects the collapse of protostars. Thank you.
Great, thank you very much. So we have time for some discussion, and maybe Melise can help moderate it to there in Virginia, and maybe Joe and Chalmers. But yeah, are there questions in Virginia first? I have plenty of questions, but please go ahead if you have.
Okay, go ahead.
I just have to, could you go back to the JWST ALMA image with the contours? So we're not seeing, or yeah, so on the right, so we're not seeing 3 different protostars. We're seeing the central protostar surrounded by the disk in ALMA, and then those dash contours are the irradiated outflow or envelope. Or are those 2 other protostars that are forming, or with those contours?
So the contours here trace the James Webb continuum.
Yeah.
Okay. So there is 2 near-infrared sources, and in ALMA there is this image of dust emission, right?
Yeah, yeah.
Okay, so and your question was?
So are those three different protostars, or is there one protostar that just one of them isn't surrounded by JWST emission?
Yeah,
is that what's going on?
So, yeah, this one, this ALMA fragment, this disk is actually.
Okay, so there is a disk behind the James Webb context.
Yeah.
Okay, gotcha. Okay, thanks.
There is a very young, fluffy
Yeah.
central point source that we can fairly call a disk here, and here. So there is four fragments that are shown in this image actually.
Okay.
And,
so unrelated to the question here about Valentin, the scattered light from the southern source there, you don't see evidence of the photosphere from that?
No, that's in. We don't see any evidence of photosphere in the southern source. We only see emission of the wind and jets. So
But if it was scattered light, wouldn't you expect to see absorption lines?
Yeah, you do. You do see. You do expect to see the photosphere, but usually, and this is what we see actually in this first survey of class 0 spectra, is that when you see a lot of emission, you don't see absorption. It's usually the rule. So it must suggest that when you see a lot of emission, you actually extincted the central core, and you're governed by the hot dust surrounding the inner disk and the hot molecular gas, and this seems to extinguish the photosphere.
Well, but there must be continuum emission from some kind of photosphere.
There is continuum, but it is very hard to disentangle in the K-band the continuum from the photosphere to the continuum from the hot disk, the hot inner disk.
Anyway, great. Other questions in Chalmers?
Hey, Valentin, thanks a lot for the nice talk. I have two questions. The first one, you said that you can, so basically like your data kind of like will match grain growth up to 50 micron, but I was wondering, like, is it possible, for instance, to have 1 or 10 micron, but with different bulk density or geometry? So my question is, like, is it possible to have like the same emission for either like 50 micron, let's say like spherical with like a given bulk density versus like 10 micron with a different geometry and a different bulk density? Do you have like this degeneracy or not? We have
it. We have definitely it. This our first first generation model, and we just assume oblong grains with no porosity, and this is indeed the next step, the next project. I'm not gonna lead it. This is more a project that will be done in Spain and France. There are people are actually trying now to implement in Polaris new dust models, implementing different level of porosity, different level of filling factor, and of shape also, and this should give a much more complete view of what actually are the dust properties probed by dust polarization. Right now, here it's just a global comparison, and we conclude that the dust grain growth is efficient, but we're not able to conclude precisely because of this degeneracy that will be addressed in future work. Yeah.
So it's still possible that you may not have grain growth efficient, but just different geometry. So it's still like open to this.
No, actually, this argument that I said is still valid for all the shapes that you want. You need to have dust grains that are large enough to see the photons, and because the photons are mostly infrared and far infrared wavelengths, to see dust grain line, you must have them at least super macrometric, because otherwise you will not be able to align them with the irradiation field that you have in the core. And because the density structures are well known, we know that the mean irradiation field is in the far infrared, right? So you must only align. You can only align large grains, and when I mean large, it's larger than 10 micron. And this is I think a solid result, because it just rely on this idea that to align the grains, you need the grains to feel the photons, to see the photons, to interact with them.
Okay, and I have like one last, sorry, Jonathan.
Can I just add a follow-up here? So this is all done at 1.3 millimeters in the ALMA side, but do you have any plans for multi-wavelength observations that would help constrain the growth?
Yeah, this is actually a very good point, and from the models we've done the last 2 years, indeed the multi-wavelengths, this polarization would be which bring much more precise results. And just using the band 3 to the band 7 in ALMA would be enough to bring more quantitative results, especially the band 3 is going to be very sensitive to that.
Better than band 1, or having not looked into band 1.
So band 1, nobody tried, because it's going to be offered in this polarization for the first time in cycle 11.
Oh.
I don't know if
okay. I see.
Jimmy, I know you have another question, but let's go to Brent next and keep it rolling. Different questions.
Yeah, Brent.
Yeah, hi, great talk. I was just curious if your near infrared data has really been able to constrain a lot about what's really going on at like the very inner part of the accretion disk.
That's indeed a thing I was super enthusiastic about, and in this first paper, we present the survey, and right now I am following up with models of the inner disk to reproduce the CO overtone emission, and I'm doing right now just 1D, 2D LT models, and eventually maybe we'll use ProDemo. But yeah, this is just work in progress. We are willing to model this prototypical inner disk of class 0 that are bright in CO to see whether we can probe the density structure, the morphology of the inner disk, whether the accretion happen via the midplane or happen via the upper layer with direct infall streams from the envelope. This is all the things we're going to constrain.
Okay, interesting.
If I may, let me ask a quick question. So Valentin, could you summarize the question about disk size, disk orientation, and fragmentation, and how they correlate with magnetic field orientation and strength? If you could give a quick summary about that point.
I'm sorry, Jonathan. I think I will disappoint you, because it's just a work in progress that and it's not ready yet, and I don't want to give like wrong conclusion, because yeah, we're just starting to do so. Right now there is one survey in Orion that was observed, one in Perseus that just got observed a few months ago, and one in Serpents that's ongoing. And on the disk size, on this disk side, same Perseus and Orion are observed and published by the group of John Tobin. We're just slowly putting things together, and there is a lot of work. Right now, the difficulties we are facing is to build precise tools to enable to build clear and precise diagnostics from the magnetic field maps. You know, and we can just compare the orientation
if you could, what about fragmentation? I mean, sometimes you have binaries, I guess. Do you notice, is that correlated with anything?
Yeah, this I think claim you tend to see binaries when you have disorganized density structure and disorganized magnetic field. And by disorganized, I mean where you see different morphology, the different orientation of the field within the ALMA field of view, for example. When you don't fragment, you usually see something more organized with a B field aligned in a given in a given configuration.
Okay.
So
that's interesting.
the occurrence of multiplicity corresponds to this level of organization of the collapse.
All right. Any other questions? We can always go back to Timmy's next question. Timmy, do you want to go ahead and ask?
Yeah, sure. So the second question I had is like, so I'm modeling like a dust evolution for class 2 disk, and as you know, like we need like initial condition from class 1, 0, 1 disks. So I was wondering, like, given the current status of your like results, what will be, according to you, a realistic initial condition for the dust size distribution?
It's hard to say because there is not even a consensus about the maximum dust grain size when people look at multi-wavelength total intensity emission or dust polarization in disks. What I can say is that it is slowly coming up together. In the envelope of class 0, as I said, we tend to probe dust grains that grew at least up to a few tens of micron, and class 1 disks have been shown to have a few tens to a few hundreds of micron in maximum grain size, and class 2 ALMA data of class 2 disks that are very abundant and precise usually claim several millimeter of maximum dust grain size. So I would say that this is evolving in the correct direction. Now one would really need to quantify the time scale of dust grain evolution with the time scale of the different lifetimes of class 1, class 2, and class 0. And also with the different density encountered in the envelope in the class 0 disk and in the more evolved disks, and all of this needs to be addressed quantitatively. And I'm not sure that actually there is a study that tried to look at it, to look at the dust grain evolution on the long-term side, starting from the envelope down to class 2 disks.
Look, Timmy may do it. That's what we've been discussing. Okay, time for one last question. Is there somebody there?
Yeah, go ahead.
You had to like skip a few talking points about the Orion bar. Do you mind if you go back and?
Sure. This?
Yeah, I think so. Yeah, I think there were a series of slides, and then you had to skip part of stuff.
So yeah, in this study, we wanted to address, to quantify this fragmentation of dust grains, but also we wanted to see if the grain alignment were the same in heavily irradiated environments. And basically, it's just it was a grain alignment mechanism study. If the irradiation field is very intense, the grain can align with the irradiation field vector and not with the magnetic field. And we wanted to check that. We wanted to see if the dust polarization probe in her big disk or in very irradiative places in PDRs running H2 regions. We wanted to see if we probe the magnetic field or the irradiation field. And this is actually this for the Orion bar, the result is shown here. You have in the histogram the position angles of the polarization. And the vertical line are the location for each box along the bar. They are the angle of the expected irradiation field. And you can see that most of the angles of polarization do not correspond to a radiation field type of grain alignment. So we kind of ruled out this grain alignment mechanism as being the dominant one. So it's, this way we can really I'm starting to be more and more convinced that we trace the magnetic field even in such irradiated regions. And this was a question that people had before. Yeah.
Very good. We should finish up soon. Well, basically, thank you, Valentin, for a wonderful talk, and enjoy the rest of your visit to Charlottesville.
Thanks, Nathan.